outline of the lectures would be, I would begin with experimental phenomenology. Then I will go on to integer quantum Hall effect theory. So this is FQHE. And I will go to theory of integer quantum Hall effect. Then I will go to Laughlin's theory. And in this context, I will derive some very nice concepts such as fractional charge and fractional statistics. And at the end, I will go on to composite fermion theory. And we'll see how these things relate to the experiments. So some of these lectures are some basic idea. It exists on the web. You can go to my web page. So let me list. So you can consult some write-up that was based on a previous set of lectures I had given, actually in a workshop conducted by the ICTS. There are also very nice lectures by David Tong. So I believe these were Infosys lectures at Tata Institute. I believe if you put in David Tong, fractional quantum Hall effect, search with those keywords, you should be able to locate those lectures. I have a problem set which you should be receiving at some point by email. So those would be things that you can just think about and work out in preparation for the tutorial at the end of the day today. The tutorial is 2 hours long, and I will be converting 1 hour of that into a regular lecture because I think having a 2 hour long tutorial just after one lecture is probably not, I mean, we don't have enough material to do problem solving. Which was discovered by Edwin Hall in 1879 at Johns Hopkins University. He discovered that in the presence of a magnetic field, if you apply an electric field in some direction, current actually flows in a direction which is perpendicular to the plane containing the electric and magnetic fields. And he defined a quantity that's called the Hall resistance, which is equal to the voltage across the current path divided by the current. And from simple classical electrodynamics, one can show that this, and we will show it later today, this quantity is equal to a magnetic field divided by the density of charge carriers times E, which is the electron charge, times C, which is the speed of light. So, so the basic idea from this is that if you plot Hall resistance as a function of magnetic field, you get a straight line, and the slope of the straight line will tell you what is the, or it depends on the density of charge carriers. In fact, this is one of the standard ways of measuring the density of charge carriers. Okay, just measure the Hall resistance, and from that you can read off the density. In fact, this was also how holes were discovered, because during some of these Hall effect measurements, they found that the sign was not coming out correctly, and that was then understood in terms of holes. So this was the situation for about 100 years. Uh, about 100 years later, Klaus von Klitzing repeated these experiments in systems which are confined to 2 dimensions. And here I have shown a couple of ways of obtaining 2-dimensional systems. So these MOSFETs that you have in your smartphones, they actually have 2-dimensional gas of electrons at the interface between 2 different semiconductors. More recent experiments are done with electron system at the interface of gallium arsenide, gallium aluminum arsenide semiconductors. So I'm not going to go into the details of how or why a 2-dimensional gas occurs at the interface, but for us it'll suffice to know that there is such a system. The system is 2-dimensional in the sense that only the lowest subband is occupied. Lowest quantized subband in the transverse direction is occupied, and therefore there is no degree of freedom in the transverse direction. Electrons can move freely within 2 dimensions, but they cannot do anything in the perpendicular direction. Okay, so when Klaus von Klitzing repeated the experiment in these 2-dimensional systems, he found something very surprising. So initially, at low magnetic fields, the Hall resistance started out the way we expect. It's going up linearly with magnetic field. But at higher magnetic fields, he found that there were these regions where the Hall resistance was constant. It was not changing at all. And moreover, the ordinary resistance, which is shown by this lower curve, it almost vanishes in this region. So wherever you see a constant Hall resistance, the ordinary resistance is almost 0. It's not exactly 0, but it's exponentially small, and it's going to 0 as temperature goes to 0. So this was his discovery, and furthermore, he noticed something very neat. He noticed that the value of the Hall resistance on these plateaus is given very precisely by this formula. So it's equal to h, the Planck's constant, divided by an integer times e squared. So for example, here the value is h over 2e squared. So this was very surprising. It was not predicted by theory. It was surprising because, so first of all, you could ask how accurate or how precise is the quantization of the Hall resistance. And at this moment, the resistance can be measured to about 7 significant figures. So it's certainly precise to that level. But you can take 2 different quantum Hall samples and you can ask how equal are the resistances for those samples. And that has been confirmed to a part in 10 billion. So as far as we know, this equation is exact. In fact, this combination h over e squared also appears in the definition of the fine structure constant. It also contains the speed of light, but that's known extremely precisely. So these experiments are actually a measurement of, an accurate measurement of the fine structure constant, and that was actually already there in the title of this paper. This effect is universal. It does not depend on what sample you take, how big or small the sample is, what is its geometry. It actually does not depend to a large degree on the amount of disorder that's in there in the sample. So it's a very universal effect. Okay, so this was the discovery of the integer quantum Hall effect. It's called integer because this number I here is an integer. And it's called integer quantum Hall effect because we'll see that this number can also be a fraction in the next slide. Okay, so the basic phenomenon is quantized Hall plateaus in regions combined with very small ordinary resistance. In fact, the ratio H over E squared has now been adopted as the new unit for resistance. It's called the Klitzing constant after the discoverer von Klitzing. Okay, then soon after that experiment, so this was, I think, in 1980, soon after that, some of these gentlemen went to yet higher magnetic fields in better quality samples. And these better quality samples were these gallium arsenide, aluminum gallium arsenide samples. And they discovered something very surprising. They discovered that they discovered a plateau here where the Hall resistance is given by H over 1/3 E squared. So instead of an integer, we have a fraction. This was extremely surprising because that, again, was not anticipated by our understanding of the integer quantum Hall effect. And a theory for this effect, the 1/3 plateau, was written by Laughlin, and I'm going to, I have shown you the basic ansatz of his theory, but we'll come back to this in much detail later on. And it is for this that Laughlin, Sui, and Stogner won the Nobel Prize in 1998. Now it turns out that 1/3 was just the beginning. So this was the initial data. In a few years, data started looking like this. So these are all plateaus. This is ordinary resistance. So each minimum here has a plateau associated with it. Each plateau has a fraction associated with it. So fractions like 1/3, 2/5, 3/7, 4/9, a huge zoo of fractions was seen very soon. In fact, this is another such picture where I show only the ordinary or the longitudinal resistance. But remember, each minimum here has a fraction associated with it. So, I mean, to date, there are more than 80 fractions that have been observed. Experimentalists can measure various properties of the states at each of these fractions. So, for example, they can measure energy gaps, collective mode excitation, spin polarization, spin wave, various transport coefficients, etc. And so there is a huge, I mean, it's a data-rich field. It's a huge amount of data. And to this, we can also add theoretical data. So we'll see that in fractional Hall effect, one can actually, I mean, theorists can take a few particles, put them on the computer, and generate the full spectrum. So all eigenstates and eigenenergies. So you can take different numbers of electrons, expose them to different amount of field, and generate lots and lots of such spectrum. Okay, so this is the phenomenology. So please tell me, let's talk a little bit about what puzzle or puzzles it presents us with. So what questions can theory ask? Can somebody, I mean, how many questions are there? Why? So you can ask, for example, why is there fractional quantum Hall effect? Right? What else? Sorry? Excitations. Yeah, what are the excitations, for example? What else? Could you speak louder?
What are the limits in which you see the fractional quantum Hall and which limits you see integer?
Okay, so in which dimensions do we see fractional quantum Hall effect, and in which dimensions we see integer Hall effect? So experiments I showed you, they're all done for particles confined to 2 dimensions.
No, as in,
But one can certainly ask whether any of these phenomena are possible in higher dimensional systems.
no, as in, I meant in which materials you would see
Or in which materials? Okay.
the limits.
Yeah, that's certainly very interesting. And there are lots of ideas on that. So there are even ideas on how to see these things in cold atom systems, for example. So what else? See, another question one could ask is why are we seeing these fractions? Why 1/3, why 2/5, why 3/7? If you stare at these fractions for a while, you realize that they all have odd denominators. In particular, if you look somewhere here, you might say, why don't I have a 1/2? Okay, why don't I have? So one could ask the question, in fact, the theory of fractional Hall effect must answer the question of why these are the fractions which are seen, why we don't have odd denominator fractions. Why do we have odd denominator fractions? Why don't we have even denominator fractions? You could then ask, why is this much stronger? You see, this plateau is much stronger than this one or this one. So there is some sort of ordering of stability of these fractions. You could ask, why is that happening? So there are lots of different questions. You could ask, what's the role of spin? Can we have spin playing a role at any of these fractions? Okay. Any other questions that we can? So, I showed you these theoretical data. So at some level, computer data, I should say. The computer can produce data which are as good or better than what experiments would produce, because computers give us the full wave function, all eigenstates and eigenenergies. So we would like to understand what are those eigenstates, what are the eigenenergies, etc. Okay. So this is the part with experimental phenomenology. Any questions about it?
Why is this effect robust against changes in geometry and disorder and presence of defects or any other features?
That's another very good question. So why is the effect so universal? Why is the quantization so precise?
Yeah.
Okay. So that's a question we'll come to later on, but it's a question that is certainly a very valid question in light of the data. All right. So all of these questions will be answered as we go on. So the first thing we need to know is how to think about electrons in a magnetic field quantum mechanically. So we all know what electrons do classically in the presence of a magnetic field. Classically, so if an electron is going in a certain direction, and if you apply a magnetic field, then there is a centripetal force on the electron, and that will force the electron to go around in circles. So that's a classical picture we all know. Let's try to understand what electrons do quantum mechanically. And this is a problem that was solved fairly early on by Landon. Okay, we'll see it's a very simple problem. So the solutions of this are called Landau levels. In fact, it was solved a couple of times even before Landau by some but these two gentlemen, Darwin and Fack. In fact, they had solved a more complicated problem in the sense they solved the problem of an electron in a parabolic potential, which is one of the home assignment problems that you'll be doing. But I think there is a law that every effect is named after somebody who is not the discoverer of the effect. So here it's called Landon levels. So the problem that we want to solve, so we are first going to take just one electron. So we don't have to worry about interactions. We also won't put any disorder, just a single electron in a magnetic field confined to, electron is confined to 2 dimensions. So that's the problem that we need to solve. The Hamiltonian is simply given by this expression here. A is the vector potential, and we know that A must satisfy this formula. Del cross A must be equal to the magnetic field, which we take to be pointing in the Z direction. So one can make many different choices of A. They are all equivalent. They are, so you have heard of gauge invariance. They are related by some gauge transformation. The 2 choices that will be useful for us in this lecture are, one is called the Landau gauge. And here so you can easily see that if I take curl of this quantity, that gives me a magnetic field pointing in the Z direction. The other choice is called the symmetric gauge. So again, you should confirm that curl of A gives you magnetic field pointing in the Z direction. So why we are working with these 2 gauges will become clear as we go on, but let's quickly see what these 2 gauges do. So let's first work with Landau gauge. So I can make this substitution in the Hamiltonian. That will give me because the y component of the vector potential is 0 and the x component is equal to minus b times y. So that I think I should not have the factor. Okay, so if you look at this, you realize that there is no x in this Hamiltonian. So this Hamiltonian commutes with Tx. And therefore, we can immediately say that the wave function must have a form of this type. Okay. So Tx is a constant of motion. I can call Px equal to h bar kx, and I know that the wave function must have this factor times something else, which we will come to in a second. So if I apply this Hamiltonian onto this wave function that replaces Px by h bar kx, and that simplifies the Hamiltonian. So let me do a couple of steps together and write it in the following form. So here you can already see that this equation is the same except for a definition, except that I have defined a couple of quantities here. One is L, which is called the magnetic length. That's and I have defined what is known as the cyclotron energy, h bar omega c. Let's write this down here. I hope you can read the letters here. This is called the cyclotron energy. Okay, so I can further define this as h bar omega c 1/2 y primed squared plus 1/2 okay, where the definitions of y primed and py primed you can read off from here. But the main point here is that this looks just like a one-dimensional harmonic oscillator. Okay, so you could have seen this right in the beginning, because just by looking at this, you know that you get things which are at most quadratic in p and x and y. So therefore, we can see here that this has the form of a harmonic oscillator, and that thing comes out very clearly here. So we can write down the solution to this. I'll assume that you know that the solutions of a harmonic oscillator are the Hermite polynomials. So we have the solution to the problem. The energy eigenvalues of these are okay. So the energy eigenvalues have this form. This is this equation you should recognize from one-dimensional harmonic oscillator, and the wave function or the eigenfunction looks like this. So this part we had already discovered here. Now we know the part that depends on the y coordinate. Is there a way I can pull this up? I don't need this anymore. And we can also remove this. So this is the full solution apart from normalizing factors. Okay, so if you look at this, a couple of things are pretty noticeable. First of all, the energy does not depend on the wave vector kx. So typically we are used to thinking of energy as depending on kx and ky. In this case, the energy is completely independent of kx. Moreover, you find that the position of the wave function depends on kx, because there is this Gaussian factor, and from this Gaussian factor, if I, let's say, fix the value of kx, then we know that it's localized somewhere where the argument of the exponential is 0, and that is when y is equal to kx L squared. So these wave functions look like this. So let's say if this is x direction, this is the y direction, then they are strongly localized along lines like this. The positions of these depend on kx, and the extent along the y direction, it's roughly equal to a magnetic length. So these wave functions are like lines, the positions of which depends on kx, but the energy is independent of kx. So for each lambda level, you have wave functions looking like this. The form of the wave function, the form factor in the y direction depends on which lambda level you are at, and that's given precisely by this Hermite polynomial. Okay, one more thing that we'll need is, so here I just do 3 lines. You can ask how many different, what's the degeneracy of a given lambda level? Okay, so how many electrons can we put in a given lambda level? Well, that's equal to the number of, okay, how do we determine the degeneracy? Number of kx values. Good. So, so we have to ask how many different kx values are allowed within a given lambda level. And the simplest way to do that problem is to assume periodic boundary conditions. So if I say my sample goes from here to here, and I assume periodic boundary conditions, so let's say this length is L or Lx. Periodic boundary conditions would say that if I change x by an amount which is equal to Lx, then the wave function remains unchanged. So that means e to the power I kx Lx is equal to 1. So that gives me kx equals to 2 n I over Lx. So this gives us discrete values of kx for this system. The second thing we can do is we can ask in over some length in the y direction, how many of these discrete kx values fall, and that will tell me how many different states I have within this region. So let's take n going from 0 to, let's say, some capital N. So kx will go from 0 to now remember, kx tells me where the wave function is located. Okay, so so this means that y goes from 0 to a value. So I'm going to use this formula here. Kx is 2n pi over Lx. So what this tells me is that if I take length equal to Lx in this direction, and this length is 2n pi L squared over Lx, then in this rectangle, I have n states. In fact, I have n plus 1 because I started counting from 0, but we are not worrying about order 1 effects. So I have a capital N states in this rectangle, and therefore so we have the area of this is Lx times 2 n pi L squared over Lx. And therefore the degeneracy per unit area for lambda level is equal to the number of states divided by the area. So that's 2n pi L squared. Okay, so in a unit area, in each lambda level, I have this many states. Let's write it out a bit more explicitly. So thank you. So I have defined here phi naught, which is hc over E. It's often called the flux quantum, although that's a misnomer because flux is not quantized. You can produce any flux you want in the laboratory. But this is known as flux quantum hc over E. And what this tells me, okay, so this is the flux through a unit area, okay, divided by flux quantum. So it tells me that the number of states in each lambda level is equal to the number of flux quanta penetrating the sample. Okay. Any questions on this? Okay, let's quickly do this symmetric gauge. So here I am going to simplify my life by setting L equals 1 and h bar omega c equal to 1. You can always put them back in the final expressions just from dimensional considerations. So with this, the Hamiltonian is written as follows. So you can try to solve it, but it turns out that this takes a simpler form if I define this quantity. Okay, so I have defined a Z. And I can also define Z bar. And you know the fact here that I have to define Z as X minus IY, it's just to simplify my life, I could have defined this. I could have defined Z as X plus IY, but then I would end up with lots of Z bars later on in my formulas. So this is the way we are defining Z. Then you have to do some algebra, which I'm skipping, but I ask you to do the algebra. You can show that this Hamiltonian can be written in this form. So here, when I write del, that means del by del z, z. So instead of x and y, now I'm working with z and z bar. And please do this algebra to show that this can be written in this form. Then we can do some more algebra. To write it in a much simpler form that brings out the connection with the harmonic oscillator. And for that, let me define some operators. Okay, so I have defined a bunch of operators, B dagger, A dagger. So some of these steps which I'm leaving out are part of the tutorial because it's a good exercise to work these things out. But you should be able to work out that the commutator of B and B dagger, is there a question? No. Is 1. The commutator of A dagger is 1, and all other commutators are 0. So if you calculate the commutator between AB or A dagger B, A dagger B dagger, whatever, they're all 0. So these are the only non-zero commutators. So now, in terms of this Hamiltonian will take this very simple form. Again, this is some algebra that you should work out, but it's equal to A dagger A plus a half. Okay. So you can see that this is just like a simple harmonic oscillator. A dagger, these are the ladder operators. And we know how to construct all states for a harmonic oscillator. If you had just one harmonic oscillator, then you can construct a state okay, that's the way to construct states. Here we have two harmonic oscillators. We have A and B. So the states would have two integers. They would be labeled by two integers. I will call them N and M. Okay. Now, it will become clear in a second why so this quantity goes from 0, 1 to 3. So why I have written it in this fashion, I will see in a moment. And the energy depends only on n. Okay, so remember, this does not contain any b. So in fact, it's the b degree of freedom that gives us degeneracy. So energy depends only on the n index, which is the lambda level index. Okay, so with this, we can actually write wave functions in real space by using the following trick. So you ask what is 0, 0. You see, we know already the form for these operators in real space. Okay. Although you can work with just the operator algebra, but we know how to write these operators in terms of x's and y's, or z and z bar. So we need to know what this quantity is, because if we know this, we can just, it's just a question of applying these operators many times to get the actual wave function. This has the property that if I apply A onto this, it gives 0, or if I apply B onto this, I should get 0. So this is the lowest state. This is a state that's annihilated by both A and B. So with this information, you can show that this is given by e to the power minus 1 over 4 z bar, and I can even normalize it. So let's see if it satisfies one of these two equations. You can check for the other equation. So let's apply B onto this. So for B, I have this expression z bar over 2 plus z del. I hope it works out. Yeah, it's 2 del. I was thinking maybe the whole thing I have done is wrong. It's 2 del. So you can see that this gives you 0. Right? And similarly, acting A onto this gives you 0. So this is, with this substituted here, I can construct the full spectrum for all lambda levels. Now let's just try to see what happens in the lowest lambda level. So in the lowest lambda level, I choose n to be 0, and I choose m to be whatever, an integer. All of these states have energy which is 0 plus a half. Okay, so they all lie in the lowest lambda level. The form of this is given as follows. So I have to apply B dagger, which is z over 2 minus 2 del bar. So I'm not worrying about the normalization constants. X on So you see, if you act with a single power of del bar, it pulls out a factor of z. So let's ask what happens when I apply just one of these factors. You can see that you get a factor of z. Okay. Then when you apply this again, it commutes with the factor of z. and again acts on the exponential, it gives you another factor of this. So basically this whole thing is proportional to z to the power m, e to the power minus 1 over 4 z bar. And let's see, I can give it a name. So we are going to make use of this later on. So the wave functions, the single particle orbitals in the lowest lambda level have very simple form. There is this Gaussian factor which is always there, no matter which lambda level you're in. But if you look at, so if you ignore the Gaussian factor for a moment, the wave functions in the lowest lambda level, they involve only z. They do not involve any z bar. Okay? So sometimes people say they are analytic functions of z. Okay, I will, yes. This is, so by putting m equals 0, 1, 2, 3 up to infinity, I span the full Hilbert space of the lowest lambda level for a single particle. So in general, if you want to write any wave function in the lowest lambda level, you would say that it will have a form where this f is some analytic function of that. Okay? All right, let me derive a couple more results which I am going to need for later. So one thing is to give a meaning to this integer m. So I'm going to show that m is nothing but the angular momentum. So the only relevant angular momentum here is the z component of the angular momentum. So I'm just going to call it L, okay, because we don't have any other components for the angular momentum. And this is minus I h bar del del theta, where theta is the angular variable. So again, please do some algebra to show that this is equal to minus h bar okay, so you have to change variables from r and theta to, I mean it's, okay, so please complete the algebra here and then do further algebra which is minus 8, it's equal to this quantity. Okay, so you will need to use the expressions for these ladder operators that I wrote on the right hand side of the blackboard. So these are equal, and notice that for the wave function that we have labeled as n comma m, the expectation value of b dagger b is m plus n, and the expectation value of a dagger a is n. So the right hand side there this for it's equal to m. So this m is called the angular momentum variable. I mean, the way these equations are written, m goes from minus n, okay, because this quantity, goes from 0, 1 to 3 onward. So therefore, m goes from -n plus 1. Okay, let's very quickly derive a couple of other results in this geometry. You could ask, what's the degeneracy? Okay, so if you let's consider the lowest lambda level for the moment. So the wave function in the lowest lambda level has the form z to the m. So what does this look like? Where is this wave function maximally located? Well, to do that, you take mod square of this and find the extremal point. Okay? Take derivative of that with respect to r. So this guy is like, has a circular shape. Its radius is square root of 2m, and I'm putting back the length scale. That's a magnetic length. So you can get that just by taking derivative of this and setting it equal to 0. So it looks like this. Okay. Now you may say, well, this wave function looks very different from what we had in the Landau gauge. There it looked like straight lines. But that's only a matter of choice of gauge, because all of these wave functions are degenerate. We can mix and match them to produce many different kinds of shapes. So these wave functions there can be written as linear combinations of these wave functions. Okay, they all describe the same physics eventually. But degeneracy can be gotten straightforwardly because in this area, I have m states, right? So because states begin with 0, 1, 2, 3. So in an area of this, I have m states. So degeneracy per unit area per lambda level is equal to m divided by this area. And this area is pi square root of 2m L squared. And you can see that it gives you the same equation as what we had before. So in a home assignment problem, you will be working out what the wave function looks like in the second lambda level. Just straightforward algebra. But let's ask, and this is something that's again going to be useful later on. Let's ask, what is the wave function of one full lambda level? Now, in this geometry, if you really want to fill a lambda level, you really need an infinite number of electrons because this lambda level goes all the way. But let's imagine a situation where we have a disk, our sample looks like a disk, and we want to fill all the states inside that disk. So that means I fill all of these states up to some radius, and I want to know what is the wave function of this state. Okay, so this clearly has, did I define filling factor? I did define filling factor. Okay, filling factor is number of filled did not define filling factor. It's called nu universally, and it is equal to how many lambda levels are full. Okay, that's called the filling factor. So I know degeneracy per unit area per lambda level. If I know what is the density of electrons, and I'm going to call it rho, I divide it by the degeneracy per unit area per lambda level. And that's the filling factor. So these are all same equation, written slightly differently. What you can see from here that the filling factor is inversely proportional to the magnetic field. As you raise the magnetic field, filling factor goes down. That's because as you raise the magnetic field, there are more and more states available in each lambda level, so you can pack more and more electrons in each lambda level, and therefore the number of filled lambda levels decreases with filling factor. So let's look at filling factor 1. And ask what is the wave function. So let's see what states are filled. So I won't write the Gaussian factor. So this we'll put at the end. Let's just worry about this polynomial factor for now. So the states which are filled are z to the 0, z to the 1, and z to the power m. Or let's say if I have n electrons, I fill every circular orbit from 0 to n minus 1. Okay? And I have electrons, so they satisfy Pauli principle, and I won't worry about spin. Let's assume that they all have the same spin, so the spin part of the wave function is trivial. It's up, 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 up everywhere. So the orbital part has to satisfy antisymmetry. So what do I do? How do I write the wave function of this many-body state? Yeah? Slater determinant. So in fact, this is, let me call it phi 1, where 1 is the filling factor. The Slater determinant would be and there is some normalization factor here, and we have the Gaussian factor. Okay, that's the wave function. Now this Slater determinant actually has a name. It's called Van der Monde determinant. There are at least two ways to write. I mean, so we have written the wave function explicitly, but it turns out we can write it a bit more simply. So one of the ways is something that I am leaving for the home assignment, for the tutorial session. So you have to do some row operations to derive the form for this, which I'm going to derive in a more, in a simpler way. So we want to write this in a simpler fashion. Again, let me not worry about the Gaussian part here. See here I'm going to use the fundamental theorem of algebra. So it says that if you have an analytic function of z, and let's say the degree of this function is k. So that means you have some so the largest power of z that comes in this function is k. Let's say you have a function like this. Then the fundamental theorem of algebra tells us that this function has precisely k zeros. You know, if you find it zeros, they have precisely k of them. Okay? So I'm going to use this. So if I look at this determinant as a function of, let's say, z1. Okay, so I'm going to treat z2, z3, etc. just as some numbers, some variables. I treat it as a function of z1. The degree of this polynomial is n minus 1, right? Because that's the largest power of z1 that occurs. So imagine you expand this determinant, you write it as a function of z1. So the degree of the polynomial is n minus 1. We know there are n minus 1 zeros. Do we know where the zeros are? Yeah? Yeah, the 1 0 is when z1 is equal to z2. Another is when z1 is z3. So zeros are sitting at other particles. So I know that this should have factors like z1 minus z2. And this actually exhausts all the zeros. Okay? It exhausts all the zeros. Because there are n minus 1 zeros and there are n minus 1 particles. So there aren't any other zeros. But now I should do the same thing for z2. Z2 sees zeros on all other particles and so on. And therefore, this wave function looks like this, apart from normalization factors or signs of plus and minus 1, etc. And of course, we have the Gaussian factor. Okay, so this Van der Monde determinant has a very simple form, and we are going to make use of this later on. So any questions? So this completes the part of the two of lambda levels and the two gauges that I introduced. Any questions on the stuff so far? Okay. All right. So this brings us to the next topic, which is integer quantum Hall effect. So I'm going to do that relatively quickly because that's not the main, that's not the emphasis of these lectures. But still, knowing how integer quantum Hall effect is explained is crucial for the understanding of the fractional quantum Hall effect. So let's begin with just a classical Hall effect. So here you have solved the problem of a charged particle in a crossed electric and magnetic field. So So you have done that problem, and you may remember. So let's see. I'm taking. Okay. So let's say the electric field is in this direction. The magnetic field is in this direction. Then the actual trajectory of the charged particle depends on the initial conditions. So it can go like this or it can go straight. But the main point is that it has a drift velocity, and the drift velocity has a very simple form. So it has a drift velocity going along the x direction. So perhaps the simplest way to see that is to just look at the Lorentz force law. And if you look at a particle with this drift velocity, then these two terms cancel. So there is no force, and therefore the particle just continues to go in the x direction with this velocity. Okay, so let's ask what is the Hall resistance. So the current density is charge times rho times velocity. Let's do in any dimension. The Hall resistance, so I'm here defining Hall resistivity. Okay, not the Hall resistance. We'll come to Hall resistance in a second. Hall resistivity is defined as Ey divided by Jx. And so Jx has an Ey in it because the velocity depends on the electric field. So you substitute these quantities here and you will end up with this relation that I had shown on one of the slides. Okay, so all I have done here, this is the definition for the Hall resistivity. Here I substitute for Jx this quantity with V given by this equation, and I get the quantity on the right hand side. Now let's consider a two-dimensional system. And let's say this is my x direction and the width of my sample is some w. And now I'm going to write an expression for Hall resistance. So that's Hall voltage divided by current. Hall voltage is given by what? If I know the electric field, it's just electric field times the width. And the current in the x direction is Jx times the width. So in fact, the width cancels out, and we end up with the same relation for the Hall resistance, which is P divided by rho. And let me put E, C, and in the formulas that I'm writing, I'm not going to worry about the sign, overall sign. If you want, you can keep that. Okay. So let's look at what happens to this when the filling factor is integer. Let's consider that situation. Now I had a formula for the filling factor. Here. I'm going to, so it's rho divided by so that's equal to an integer. So what I'm going to do is for rho, I'm going to substitute this equation in the first equation. So Hall resistance from here is B divided by rho. So for rho, I'm going to put N D over phi naught EC. D cancels out, and phi naught is HC over E. So this gives me H over N E squared. Okay, so if I take the filling factor to be an integer, I find that the Hall resistance is equal to H over that integer times E squared. So you may feel very happy. You may say, okay, I got this formula that is the formula for the Hall resistance on the plateaus, except that there is a problem here. If I keep the filling factor to be general value, not an integer, then I would find that the Hall resistance in general is H over nu E squared. Okay, so I mean this is not surprising. You know, we classical considerations cannot explain the quantized Hall effect. So again, from classical formula, we find that the result agrees with the observation precisely when the filling factor is an integer. In other words, let's plot this here. So quantum mechanically, we find it goes like this. Classically, it goes like this, and at integer values, the two agree. But the classical result still is a straight line. It depends continuously on the magnetic field. So this does not give us the presence of the plateaus. Okay? So that's what we need to explain. Okay. So I have about 7 minutes. See, it turns out that this formula is very powerful. The classical formula is very powerful. You might actually argue that this formula is correct even in a fully quantum mechanical theory, and you can argue in the following fashion. So we know from theory of electromagnetism that if I have crossed electric and magnetic fields, I can boost myself to a moving frame of reference where there is no electric field. Okay? And the moving frame of reference is the frame where the velocity is precisely this, CE over V. So imagine I go to that moving frame of reference. There is no electric field, so electron is just going around. There is no current overall. It's just going around in circles. All electrons are going around in circles. There is no current. So therefore, I can come back to the laboratory frame of reference, and the current is precisely given by this. Okay. So even in a fully quantum mechanical theory, that's what I would find, and therefore I would conclude that there are no plateaus. The Hall resistance will be just a straight line. So what's going on? Well, the thing that we have to take into account, and perhaps that's a little bit surprising, is disorder. So in making this boost to a moving frame of reference, we have assumed that the system is translationally invariant. But in general, if we have disorder, then that argument fails. So let me very quickly say in the last few minutes of this lecture what we expect disorder to do. So I am not going to go into detail, just give you a very simple pictorial description of the role of disorder. So let's imagine a two-dimensional system with no disorder. And now let me put on top of this a potential hill. And let me ask what this is going to do. So to simplify things, I will assume that this is a very smooth potential hill, which means the change in this potential is very slow compared on, it's very small on the length scale of a magnetic leg. So therefore, locally, lambda levels, etc., are well defined. So the energy of this system in the lowest lambda level is 1/2 h power omega c plus the potential at the position r. So this is the energy at any position r. Okay, I can just define lambda levels locally, and this is what I would get. And therefore, to conserve energy, the only thing electron can do is move on equipotential contours. Okay? And in fact, you know that it's going to move on these contours because this potential is going to create an electric field. Okay, so this electron is now seeing crossed electric and magnetic fields. It's going to move in the perpendicular direction, which is exactly following these equipotential contours. And therefore, this electron now is going to get localized around this edge. So we know how many particles or how many states we have in this region, and that many localized states you will have. In fact, potential hill localizes electrons, so potential well will also localize electrons, because here the electron is going to go around the localized equipotential contours around the potential well. So the picture that comes out is the following. So if I draw the density of states, let's do it this way. As a function of energy, earlier we had only these energies available. This was 1/2 h per omega c, this is 3/2, 5/2. These are the only energy scales available, nothing else. Now with disorder, these guys have slightly higher or slightly lower energies. So the lambda level broadens like this, and the states that are here in this region, they are localized, just by this picture that I showed. So the picture that we have, which will be crucial to explain the integer quantum Hall effect, is that we have extended states here, and we have localized states here. So we have the density of states broadens. It basically extends to all energies, but the states in between the original lambda levels, they are localized. Okay, so we'll see in the evening how this leads to quantized Hall plateaus. Any questions on this so far? Precisely. Exactly. It's like Fogg-Darwin problem. So that's precisely the point. So initially I had made states of this type, which were all degenerate in the absence of any disorder. Now if I put a potential hill here, then these states are not going to remain degenerate, and that's why they pull away from the unperturbed lambda level energy. Any other comment or question? Yeah, so, so it is believed, and there is experimental evidence for it, that extended states exist only at one energy, which is the energy of the unperturbed lambda level. Of course, there can be many extended states, but they exist only at one energy. So it's believed that as soon as you go away from this, all states are localized. And this has been supported by numerical calculations. So you can take different kinds of disorder. You know, I took something that's simplest to visualize, but you can put delta functions, scatters, random impurities, and so on. They all seem to be consistent with the idea that there is that extended states in an infinitely large sample exist only at one energy, or only at these energies, at the center of each lambda. All right, so we'll meet again in the afternoon. Thank you.